Hey, what's up? It's Miss Wesley. Excited to talk some more trig with you, and we get into some exciting stuff about radians today. We're looking at Trig Packet, page 19 for starters, and today you get two jokes for the price of one. The first one is, why does Where's Waldo wear stripes? Well, because he doesn't want to be spotted. And what happened to David after he lost his ID? We had to start calling him Dav. It says radian measure here, and we've been talking about angles and the unit circle that you're going to see a little bit further down the page for the last couple of lessons. But there is another way to measure angles, and that's in radians instead of degrees. And that's a really important way to measure angles, and you're going to see it coming up in all your future math courses. It says, take a look at the circle to the right. Imagine taking the length of the radius, so you've got the radius here, about this length, and you can wrap it like a string around the circumference of the entire circle. And the first challenge is, how many of these radii do you think will it take to fit around the entire circumference? I don't know, let's try it. This is going to be a rough estimate, but here's one time, right? Can I take that same length and do it again? Here's twice. I'll just put a 2 here. Here's about 3 times. We've almost gone halfway around the circle. Here's about 4 times, I guess you could say. I'll put a 4 there. Here's 5 times. We're coming up on the end here. So I'll put a 5 here. Here's 6 times, which I think doesn't quite do it. 6 and a little bit of change. So a little more than 6, 6 point something. And I wonder if this is going to become an important measure. So a little less than, or a little more than 3 to get halfway around the circle, and a little more than 6 to get the full way around. Well, let's define radian measure. It says 1 radian, and it's named a radian because it has a lot to do with the length of the radius of any size of circle. It actually didn't matter that this circle was this size. We could have made it bigger or smaller and done the same type of experiment. So it says, is the measure of the central angle theta that intercepts an arc S equal in length to the radius of the circle? So it's exactly what we were just talking about. If the radius is this length, right, 1 radian of measure, this measure theta, is going to be the angle cut off when this arc is the measure of the radius. And you can see a much better diagram down here of how it would look to stretch that radius around the circle. It doesn't matter what size circle you have, every single time it's going to fit around a little bit more than 6 times. And I'm dying to give you the conversion here, because if I look at this unit circle that we've seen before, we've worked with everything on here besides what you see, these measures that are in terms of pi. These are the radian measures. So we know, in quadrant 1, you've got special angles, 30, 45, 60, and you've got all your quadrantals all the way around. But I'm looking at these pi over 6, pi over 4, pi over 3. I want to come up with a good way to be able to, if we feel comfortable enough with degrees, I want to feel just as comfortable with radian measure. Another thing you're going to find, and why I'm so excited about this, is radians are very, very visual. You can kind of look at a circle and split it up in terms of, you can almost make the joke pieces of pie. But down here, this is important. This is a measure of, let's say, 1 degree. 1 degree always gets units with it. So 1 with a degree sign is equivalent. Would you agree with this? It's a rotation of 1/360th around the circle, right? Because if I had 360 degrees, I would have made it the whole way around. Well, 1 complete revolution corresponds to 2 pi radians. So remember I was saying a little bit more than 6 gets you the whole way around? If pi as a decimal, I'm just going to put like a 3.14 here. I know that's not exactly pi, but it's rounded to the nearest hundredth. Well, then 2 pi is a little bit more than 6. About 6.28 gets you the whole way around the circle. And that's going to happen every single time. 6.28 is a good approximation for how many times that radius would fit around. And this leads us to some nice, easy conversions between radians and degrees. If 1 complete revolution equals 2 pi radians, then 360 degrees gets to equal 2 pi. And if you don't want to have that equation, doubled like that, if you'd like to reduce it, you can divide both sides by 2 and get that 180 degrees equals how much pi? Should just equal 1 pi. So it's kind of funny. A full circle is 2 pi. So where's the 2 pi here? I guess it's not written, 2 pi. A half circle, a semicircle, gets you around 2 pi. and we can split it up. I mentioned something about radians being very visual here. We can split up this half circle kind of in thirds and fourths and sixths. So let's take a look. Let's first try to convert. If we want to convert degrees to radians, what we're going to see in the first set of examples, just take the degrees, multiply them by something that equals 1. Pi equals 180 degrees. So if we multiply this degree measure here, 30 degrees, by pi over 180, we will have its measure in terms of radians. And for this, some of this we're going to reach to the calculator for, but for this one, just reduce by hand. We can leave pi in our answer. So 30 goes into 180 6 times, right? We get pi over 6. And that is, let's see this visually. On the unit circle, 30 degrees is 1/6 of the way over to a full pi like that. So 1/6, and then you'll see the others going around. Let's just write this here so we can use it for later. If we have radians and we want degrees, we can flip that fraction. We can multiply by 180 over pi. So this you'll see us using a lot today, especially if you felt pretty comfortable, like I said, with degrees. It's nice to convert radians to degrees and then have a better feel for where the angle's going to fall. Let's try some other common special angles, like 45 degrees. Same exact conversion rule, 45 times pi over 180. And we can reduce, 45 goes into 180 4 times. You're going to end up getting a pi over 4, like that. How about 60 degrees? We should know this one. Is it much of a surprise that I think when you try this one and you reduce and you leave pi in your answer, you get pi over 3? Is that much of a surprise? Well, no, if I look at the circle that's above, because I can see it there, 60 degrees equals pi over 3, but I should have been able to guess that. If 30 degrees was 1 pi over 6, if I double that for 60 degrees, I should be at 2 pi over 6. So I can double my answer for number 1 to get my answer for number 3. How about 90 degrees? For this one, I just want to look visually, right? If a whole, let's say a half circle here, is pi, right? Halfway there, pi over 2 should be where 90 falls. And you can do the same thing by multiplying by pi over 180. You get pi over 2. Okay. Now, what about this one? Okay, so I gave you some kind of crazy decimal. I know 249.546 falls somewhere in quadrant 3, right? And we can use the same conversion, but here's where I'd say your best bet, it's not going to be a pretty value. I'd say your best bet is to approximate with the calculator. And I'll be pretty specific on a quiz or a worksheet whether I want you to leave pi in your answer like it was convenient for 1 through 4, or just use the pi key. So why don't I try it? 249.546. 546. I'll just use the pi key in the calculator, so times pi divided by 180. And we'll round this maybe to the nearest thousands. 4.355. 4.355, and we'll say radians. The cool thing too is you notice I didn't put units after any of these. I could put RAD, so everybody knows that I'm working in radians, but the lack of units here implies that you're working in radians. And that's why it's doubly important that when we convert to degrees in 6 through 10, we do put units on our answer. If you mean to tell me, so for number 6, I look up to my conversions, and when I want degrees, I want the pi in the bottom of the fraction. So I'm going to multiply by the reciprocal of what I was using before and use 180 over pi. What's great is the pi's get canceled, and you can multiply through. If you'd like to reduce a little bit more before you get going, I'd say that's a good idea. So I could see that 3 goes into 180 60 times, and I end up getting 2 times 60. I end up getting 120. I need to put degrees after it. Without the units, like I said before, it's assumed to be in radians. So all these 6 through 10 would need units. What about 7? 5 pi over 6. So I'll multiply by 180 over pi. I'll either use a calculator or just in my head reduce. 6 goes into 180 30 times. What do I have left over? 5 times 30 gives me 150 degrees. 3 pi over 4, let's check it out, times 180 over pi. Get the pi's to cancel. 4 does go into 180, so 4 goes into 180, I think 45 times. And 3 times 45, let's see what that is, 135 degrees should do the trick. 8 pi, it's a huge angle. You know, I think we could get this one or an equivalent just visually, but let's see if we could do this the same way. If I did multiply by 180 over pi, okay, I know the pi's still cancel, and I have to put down the huge degree measure of 8 times 180, so I get 1440. What's funny is, man, if I found a couple coterminal angles to this, so I know that's a lot of times around the circle. If I subtracted, I think 4 360s from this, I would be down to 0 degrees. This angle falls in the same spot that 0 degrees falls. Take a look at the unit circle. Let's confirm it, right? Here's 1 pi, 2 pi, we're back to 0. 3 pi, I'm over here. 4 pi. 5, 6, 7, 8. Any even multiple of 2 pi, integer multiple of 2 pi, is going to land you in that 0 degree or 0 radian spot. There's one more on the page. 10, it just says, it's the only one in the row that doesn't have a pi in the original problem. It just says convert the radian measure 4. Well, you know what? You do this one the same exact way. We'll multiply by 180 over pi. And in this one, I would specify in the instructions, but I'm going to have you go straight to a calculator and we'll use the pi key, get a decimal. So we'll make sure this makes sense. 4 times 180, this time divided by pi. Hit enter. I'll write it down. 229, we'll say 0.18 degrees. So 229.18 degrees. Are you buying it? Does it look good that it would fall? Where is this in quadrant 3, right? 4 radians. Here's 0, here's half pi, it's about like 1.57, that's half of 3.14. Here's pi, and then if you go to 3 pi over 2, if you add a half pi to that, you get to 4.71, right? You're a little past it. This is a quadrant 3 angle, and we need the degree sign after it too. The last thing I'll say before leaving this, because conversions are so important, the only thing I sometimes mix up is I'll just forget when do I use the one with the pi up top, like these in red, and when do I use the one with the pi on the bottom. Frequently, do you see these starting out radian measures? Frequently, we're going to have radian measures that have pi in them. So when you want radians, right, it's good to leave pi in the top so pi goes in your answer. When you want degrees, right, like in these blue examples, I usually don't, it's kind of weird to say 5 pi degrees. I haven't heard anyone tell me something like that. So you generally want the pi to cancel, which is why it's smart to put the pi in the bottom of the fraction that time. Let's see what else is here. Okay, so a couple sketching questions, and we'll skip around these. It says, can you sketch an angle of 2 radians? Well, sure, if I've got some decimal approximations here, it shouldn't be too bad. Here's 0 radians. Here's pi over 2, right? That's about 1.57. Here's pi, it's about 3.14. And this one is 1/2 pi, 2/2 pi, 3/2 pi. This will be 3 pi over 2, which is about 4.71, before I get back to the ending point, which is around 6.28, 2 pi. So that should help with all 3 of these. 2 radians is between. Just pick a good quadrant for me, right? Initial side, terminal side, past half pi, but not quite to pi. So 2 radians is going to fall somewhere in quadrant 2. Do you have a quadrant for 4 radians? Sure. We've passed pi. And we haven't quite gotten to 4.71, just landed somewhere in quadrant 3. 5, right? Looks like we have a quadrant 4 angle, because you're not quite to 6.28. You're down there in quadrant 4. Now I want to actually be real careful with 14, actually with the rest of them. Can you, because soon we'll be talking about reference angles, and I do want to count around the fractions. Can you try this with me for 14? Let's try to get a really accurate picture of this. Count in thirds pi. Can you split this up? If this is 0 and this is pi, here's 1/3 pi. Here's 2/3 pi, right? Then you have 3/3 pi. Here's 4/3 pi, and then 5/3 pi. You're going to see over here, 5 pi over 3. It's just like you split the circle up, right? Split the pi up into thirds and then count to 5. 1, 2, 3, 4, 5 should land me in quadrant 4 without having to convert. If I did convert, I'd multiply by 180 over pi, and I'd end up getting 5 pi over 3. I'd end up getting, I think, 300 degrees, which confirms quadrant 4 is a good quadrant for that. Stay tuned for the next segment where we'll practice with a few more of these. Talk to you soon.